This video will begin our series on override control. In general, you map one controlled variable with one manipulated variable. However, with many systems, there are more controlled variables than manipulated variables. Therefore, when a system arrives at an abnormal condition and a controlled variable goes outside its desired limits, then manipulated variable needs to be used to drive this controlled variable back into its normal operating range. You will see among systems such as reactors or distillation columns that certain manipulated variables have many override controllers associated with them, since these manipulated variables impact many controlled variables. So now let's start off with this following example. Suppose they're using cooling water to control the temperature of the reactor. So the cooling water is pumped into the reactor, goes to the reactor jacket, where it absorbs some of the heat from the reactor and then is returned back to utilities, most likely. So as you increase the controller output of this cooling water valve, you would decrease reactor temperature as well as cooling water return temperature. In this example, reactor temperature is your normal operating control variable, while cooling water return temperature is your abnormal operating control variable. Your cooling water valve is the manipulated variable used to control both these controlled variables. Cooling water always contains minerals whose solubility decreases with temperature. Therefore, the hotter the cooling water, the more fouling that will happen within the reactor jacket. So, cooling water return temperature is an equipment protection control variable. On the other hand, the higher the reactor temperature, the higher the conversion rate. Therefore, there's a trade-off between these two variables. You want a high cooling water controller output for the cooling water return temperature. On the other hand, you want a low cooling water controller output. You want less cooling water for a higher reactor temperature to increase conversion for the reactor. Since reactor temperature is a normal operating control variable, then you want the cooling water valve to be moving to optimize this variable most of the time, for the most part. While you want a high set point override controller for the cooling water return temperature. Since you want a high set point override controller, you don't want this cooling water to be too hot, so you need a high set point override controller. And this control variable has a negative gain. It has a negative gain because as I increase the valve, I decrease its temperature. So there's a negative, or I guess an inverse relationship between these two variables. So again, since you need a high set point override controller, and there's a negative gain between these two variables, then you need a high select function block to accomplish this, as you can see in this figure here. So we will explain this matrix, the set point and gain matrix, in the following slide. Suppose I have a tank. It has an inlet flow. There's also outlet flow. If the inlet valve is open more, while you keep this valve the same, your tank will start accumulating level. Concentration mass, if I have more going in than going out, then my level is going to start accumulating. On the other hand, if I open up the outlet valve more while keeping the inlet valve the same, I'm going to have more going out than what's going in, then this level is going to start decreasing. So now let's assume that we put a high level override controller on this inlet valve. So this level goes above set point. Then we would want this controller, this override controller, to cut back on this valve, because if you further increase the amount of flow going into the level, then it could potentially overfill the tank. So you would want a low select block, because you would want to cut back on the inlet flow. So if you have a positive gain, which means, hey, if I increase this valve, then my level is going to increase. So I have a positive relationship between, hey, if this increases, this also increases. Therefore, there's a positive gain between these two variables. And I have a high set point, so I want to cut back on this valve if the high set point gets exceeded. That means I want a low select block. So now let's suppose this controller has a low level override controller. So you have a low level set point, the level goes below that set point, let's say like down here. You'd want to start increasing your inlet flow. Therefore, you want a high select block. Now, let's suppose that you have a high level override controller for the outlet flow. So hey, my tank is getting too full. I want to increase this outlet flow. So I have a high set point negative gain, therefore I want a high select block. Let's assume that we have a low level override controller for this outlet flow. My level is getting too low, that means I'm taking too much out of the tank versus what's coming in. Therefore, I would want a low select block. I want to decrease the controller output of this valve. Again, going back to our example, we have a reactor with cooling water that's going in, and TT2 is that cooling water return temperature sensor that is sensing, hey, what's the temperature of this cooling water coming out of the reactor jacket. Our primary, or I guess more appropriately, our normal operating control variables are reactor temperature, TC1, while our abnormal operating control variable, which is used to protect the reactor in order to not have fouling within the reactor, is this cooling water return temperature. And since it's the abnormal control variable, then this one is the one with the associated override controller. Both diagrams show the cooling water return temperature controller override the reactor temperature controller. Let's first focus on the graphs within the red square. So these first three graphs. From time 0 to 120, the cooling water return temperature is below set point. Therefore, it's calling for the cooling water valve to shut because it's too cold. This cooling water valve goes, hey, I need you to shut, 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 until it finally exceeds its set point here. However, this controller is not in control. The reactor temperature is controlling the cooling water valve. Thus, the integral error will continue to accumulate, which causes this controller to wind up. Once cooling water temperature is too hot at time 120, now the cooling water return temperature controller wants this valve to open. Therefore, from time 120 to 140, the cooling water temperature controller output increases and then finally overtakes control at time 140 right here. So we have a high select block. Preferably, we would want the cooling water return temperature override controller to take control once the cooling water temperature just crosses its set point at time 120. However, the integral error was so large that it took the controller 20 minutes to finally supersede the reactor temperature controller here. So now if we examine the graphs in the green box, we observe that there's no windup. The cooling water controller output is both closer. I guess what I mean closer is that this distance between the yellow and blue line are much less, and it's gradually getting less as this cooling water return temperature approaches set point. You can see that the distance between these lines is changing. While we go back to the red box, look at the distance between the yellow and blue lines here. It's changing, but the blue line is not moving closer. It's only the yellow line. So the blue line's really not tracking. It's just staying at the same value. While both of these values are converging. So at time 120, the cooling water return temperature finally overtakes reactor temperature. Okay, so the cooling water temperature control output is both closer and tracking reactor temperature controller output, even though the cooling water temperature controller wants the valve to close to converge at set point. So yeah, naturally you would think, hey, since the cooling water is below set point, this should be at zero, or it should be, hey, this should be going down right now pretty quickly, because this has been low for a while and there's no response between its controller output and its PV. Therefore, something needs to be changed in order for the case in the red box to not happen. So to prevent windup, the integral portion of the PI controller for the cooling water return temperature is replaced with the reactor temperature controller output to prevent windup, so that the cooling water return temperature can track the reactor temperature controller output. We can see the removing the integral portion and replacing it with the controller output that is currently controlling the valve changes several things. One, the reactor temperature starts to diverge from set point at time 120 instead of 140. So we can see back in the red box that the reactor temperature from time 120 to 140 was still controlling temperature. So it didn't actually diverge from set point until that time 140 when the cooling water valve, or excuse me, when the cooling water return temperature controller overtook the reactor temperature controller. While at time 120 here, since cooling water valve took control, then this set point, the reactor temperature PV, started diverging from set point. The second big thing is that there was minimum or no overshoot between the control variable, the abnormal control variable, and set point. So again, there's some overshoot here since we had windup. While here we have no overshoot since we had no windup between time 120 and 140. So the the cooling water return temperature controller can make sure at time 120, hey, let's not get this set point, let's not get this PV too high, so let's start making sure that this PV tracks its set point. And again, we already said this, but the cooling water temperature started controlling at 120 instead of 140 since there was no windup. So now this is the other case where now we want our cooling water valve to start controlling our reactor temperature, and that won't happen until the reactor temperature controller has a higher controller output than the cooling water return temperatures controller output. So again, the red box, the graphs in the red box have windup. It's the case with windup, while the green box has no windup. So now let's go over this case where reactor temperature overtakes the cooling water return temperature. So we can see from time 0 to 120, its reactor temperature is below set point. So At 120, it goes above set point, and it will overshoot since we have windup. So we go to the controller output graph. Hey, since we know we have windup, we know that the integral portion is not replaced with the cooling water return temperature control output. We know that our integral error is going to start accumulating here because reactor temperature has no control over the valve. So our reactor temperature control will wind up, as we can see here, saying, hey, I'm too cold, I'm too cold, I'm too cold, so shut the valve, 120, okay, I'm too hot. Then it's going to take a while until eventually reactor temperature controller overtakes the cooling water return temperature controller, which allows for this overshoot. Go to the green box, we can see that, hey, since we have no windup, we see the reactor temperature at 120 starts being controlled instantaneously because the reactor temperature controller is, when it's not in control, it's using the cooling water return temperature controller's output to replace the integral for this controller. So it's tracking, it's tracking, it's tracking. This between blue and yellow line are converging together. Time 120, the reactor temperature controller overtakes it. Therefore, you have this seamless transition between these two states. And then similar to the last case, since you have seamless transition between controller outputs, we can see that the control variable that was previously in control starts diverging from set point at time 120 instead of 140. So this is our first video of the series, which covered a reactor with two control variables, one manipulated variable. The manipulated variable again was the cooling water valve, while the control variables was the cooling water return temperature and reactor temperature. Again, reactor temperature is the normal operating control variable because that is the variable you want to control conversion, while cooling water return temperature, you got to make sure that's not too hot, because if it is too hot, that means you're going to have fouling within your reactor jacket, which is obviously not good. So that's our first example. I appreciate y'all watching.